Hello. Thank you for joining on this PowerPoint presentation on point-to-point and point-to-multipoint. I'm Gabriel Reyes, and I'm the sales engineer here at Ingenious Technologies.
Thank you for joining on this PowerPoint presentation on point-to-point and point-to-multipoint.
Sorry about
I'm Gabriel Reyes, and I'm the sales engineer here at Ingenious Technologies. Thank you for joining on this PowerPoint presentation on point-to-point and point-to-multipoint. I'm Gabriel Reyes, and I'm the sales engineer here at Ingenious Technologies.
that. Sorry about that. Hang on a second.
Sorry about that. Hang on a second.
Okay, so if you guys can hear me, that should fix the echo issue. Sorry about that. So without further ado, let's go into the point-to-point and point-to-multipoint PowerPoint presentation. The reason why I like to do this presentation is because in wireless, there is it's a very niche type of field in knowledge, but the outdoor point-to-point is even more of a niche type of knowledge. So it's very hard to find valuable information. And I've noticed that a lot of people I help and the customers, they really like to do the point-to-point, particularly certain verticals like security. And so we want to make sure that we do a PowerPoint presentation that covers a lot of stuff that you probably won't get elsewhere with the experience that I have. All right, so let's go over the agenda today. We're going to go over some partner benefits, the difference between point-to-point and point-to-multipoint, when to use point-to-point and point-to-multipoint, also some considerations to take in your outdoor deployment, backhaul deployment, which is Fresnel zone, antenna type, channel width, and frequency band, as well as the standard or non-standard 802.11 considerations. And then we're going to go over some examples, or one example of each, and then we're going to take your questions. Okay, so the partner benefits program, you'll find that at partners.ingeniostech.com. There's all these great benefits, and we'd like to see you take advantage of these benefits, such as dealer pricing for it, easy Wi-Fi planner, access to certifications and trainings, as well as access to this recording, which is going to be behind there as well. Without further ado, let's start talking about a point-to-point. So what is a point-to-point? Well, as the image shows on the top, a point-to-point is you have two radios connecting to each other in the backhaul type of scenario. They can either be doing, let me see, standard 802.11, they can be doing another type of protocol or something else, which we'll talk about later. We have something called a route and a non-route. So the route would be considered the one closest to the demarcation point, and the non-route would be opposite to that. It's important to note that we have a 1-to-1 ratio. So as you can see in point-to-multipoint later on, you'll have different ratios of non-route to route. The benefits of having a point-to-point is there's one contention domain. There's no other radios contending for access to the medium. It's just two radios. It's easy to set up. You just have to worry about one line of sight, Fresnel zone, and only one, want to talk about beam widths, only one of that. So you get narrower beam widths. You have to calculate line of sight. It's a lot easier to do that. It's dedicated throughput as well. So it's just like the top of the no contention. You're not sharing the capacity of the link across multiple nodes. So an example of point-to-point would be just like this example, which we will come over. We'll follow up with it later on in the PowerPoint presentation. This is actually going across two state lines. We have the non-route in the upper left-hand corner, and then we have the route at the lower right-hand corner. So they're going to send a signal from the lower right-hand corner up into the upper left-hand corner for whatever they need. So let's talk about a point-to-multipoint. So in a point-to-multipoint, we actually have several non-routes to a route, In this particular example, we have a 2-to-1 ratio, so 2 non-roots to 1 root. They could grow even more depending upon the capacity of the link. You could do 3-to-1, 4-to-1, 5-to-1. It could go even higher. The benefit of having a point-to-multipoint is lower equipment cost. In the example right now, if you were to do point-to-points, we would have 2 point-to-points, and it would require 4 sets of radios. In the point-to-multipoint, we actually have just 3 radios, but as the ratio gets bigger and bigger, like a 4-to-5, the ratio actually gets, the ratio gets bigger, the amount of equipment gets smaller. So let's say we have a 4-to-4. Well, then that would mean we would need 8 radios as opposed to only 5 radios. They're good for they're good for low to moderate network demands, and we'll go over why that is later. So basically, you have a certain network capacity, and you're spreading it across multiple root nodes. And so, if you need something that has greater capacity, you'll need to be able to shrink the ratio, maybe even bring it to point. So here's an example of a point-to-multipoint, which we did in the Seattle area. It is a condominium complex, and we were actually replacing another vendor that was mesh, and we replaced it with WDS bridge links from our in-station ACs. In this example, we have the root in Rec Building 1 in the top right-hand corner, and then we have the Building Q, P, and N, which are going to be the non-roots, and they have cameras on them as well. So the in-station AC is a 30-degree beam width, which we'll talk about later on. But as you could see here, between building Q, P, and N and Rec Building 1, that's actually a 90-degree arc there. And you'll see the reasons why we're able to get away with that. But this is an example of a point-to-multipoint. This will be a 3-to-1 ratio. Okay, so now we're getting into choosing why we choose a point-to-point or a point-to-multipoint. The biggest reason is based upon the application network metric requirements. This sounds like a lot of nothing, but it really means what is the application going down the network and how do I design appropriately for that application. For example, if I were using something that is very latency sensitive, such as real-time applications, such as terminal software, telnet, PTZ cameras, security access controls, or VoIP, I would actually most likely lean towards a point-to-point type of deployment for those, because those actually are very latency sensitive. They need access to the medium as quick as they can. They don't want to have time to sit around and wait for contention. Things that are not latency sensitive, such as IP cameras, file transfers, streaming movies, I'll mostly do that as a point-to-multipoint, so long as the capacity so long as the load doesn't see the capacity I have to give to them. Project budget is also a big thing. Remember I talked about earlier a point-to-multipoint. As you start getting the ratios higher, it gives you more of a cost savings per the devices. That would be one reason why you go to point-to-multipoint over point-to-point. The non-root count. If I have a lot of non-roots, it may be more beneficial for me to go point-to-multipoint as opposed to point-to-point due to the cost of that and the channel reuse and the amount of spacing I have to mount the antennas. Line of sight limitations. Let's say, for example, if I want to go around a building, well, then I'll have 2 point-to-points as opposed to maybe 3 point-to-points as opposed to just 1. Or let's say I have a tree in the way, and so if the tree's in the way between 2 nodes, and that may cause Fresnel zone blockage, I may do 2 point-to-points. Or let's say I want to connect to multiple devices in a row, and for them to be stacked on a tower for the roots would be too close to each other. I would do a point-to-multipoint in that situation. That would be one of the mounting location limits as well, which is the physical space you have to mount them on, as well as access to the power and easements rights to mount them, aesthetics. Sometimes people don't like to see antennas, and then also the antenna height limits. Sometimes you're limited on how high you can mount these antennas due to regulatory, whatever in your regulatory domain you have. Also, you have antenna beam width restraints as well. One thing I want to touch on that for beam width restraints right now, I want you to know is that the general rule of thumb is that the wider the beam width, the less range you're going to get from the antenna, and the narrower the beam width, the greater the range you're going to get. There's also other benefits too, which we'll go over in later slides. So now we're going to talk about the Fresnel zone consideration. Basically, this is also known as minimum antenna height. It's actually the RF line of sight requirement. There's only 2 variables that impact this equation. The equation's on the right-hand side, and it is distance and frequency dependent. So that means that this equation outcome will be dependent upon the distance or the frequency. So when I'm planning a link and I have to think about RF line of sight requirements or Fresnel zone requirements, the only two things I have to really worry about is the distance and the frequency that these two are operating on. So when it says minimum antenna height, it means the minimum height has to be above any obstacle for it to be unobstructed. Now, it could be obstructed. Rule of thumb is 30 to 40%, depending upon whatever you're doing on the network. I like to plan for 100%, and then from there you have reality. You can start seeing how much you could get with the obstruction itself. But if you could get 100% unobstructed in the real world, then I would say go for that as much as you can. The reason for that is because of the image in the bottom, you could see that there's an obstruction within this Fresnel zone. And then you see FZ1 and FZ2. FV1 stands for the first Fresnel zone, which we're the ones interested in, and FV2, which is the second Fresnel zone, which is one we're not really that interested in. So when you have an obstruction in the primary Fresnel zone 1, the radio waves, they bounce off the obstruction, maybe they get absorbed. So they come back in a way that you can't predict in different angles. They come back with different amplitudes and different phases of the actual wave. So when waves interact with each other, there's only three things they could do. They could either do something which we call constructive interference, which is they'll actually give you an application of the signal beyond the FSPL, which is called free space path loss, which we'll go into that afterwards. We have destructive interference, which is signal loss over FSPL. And then we have nullification, which basically they just cancel each other out. So of those three options, there is two that's undesirable and the one that is desirable. So as the obstruction starts obstructing more of your Fresnel zone, you actually start getting a higher chance of those two things happening as opposed to the two you don't want. For free space path loss, that's basically an equation that we have to calculate the amount of RF loss you're going to get over open air. So when I say amplification, I'm not saying it's going to be more signal than what's going to come from the antenna. It's just more signal there than what you're going to calculate in FSPL. That's what I mean by that. So I'm trying not to confuse you there. Fixes for obstructions would be to mount the antennas higher if possible, move the antennas closer if that's possible, or you could move to a different frequency as well. So the rule of thumb is for the lower frequencies, such as 2.4 gigahertz, you'll have a larger Fresnel zone. For higher frequencies, such as 5 gigahertz, 11 gigahertz, 60 gigahertz, 28 gigahertz, those have a smaller Fresnel zone because the frequency gives you a smaller Fresnel zone. So things to take into consideration for Fresnel zone is foliage changes. For example, this tree in the bottom left hand of the slide, let's say I deploy it during the winter and I get great signal strength. And let's say spring and summer come around. Well, then the leaves start growing on the tree. And what happens is the link may become marginal or it may be unusable at that point. And at that point, I have to take the tree into consideration for Fresnel zone. So that's obviously something you might want to have a look at before you deploy it to make sure you do the proper calculations to take that into consideration. High profile vehicles, you're also going to be impacting your RF signal. For example, I had a customer that had gas pumps on the far end of his gas station, and he was servicing semi-trucks, and he had his antennas mounted about 6 feet above the ground. And that was good for cars or for SUVs, but for semi-trucks, they could be up to 14 feet high, and depending on whether they're carrying metal or if they're insulated, trailers that have more insulation in them and they attenuate the signal more, they're actually when they would pull in, they actually cause the pumps to no longer operate. So the fix for that was to just move the non-root antennas up into the roof line of whatever easement was atop of that, which was like 20-something feet high, to get above those high-profile vehicles. Also, got to take into account if you're doing backhauls in RV parks, those RVs have different heights. You don't want an RV to drive through and block your signal, or block that link. Ground topology, different elevations of the ground. You have to take that into account. So if I have one at lower, one at higher, I may have to raise the lower one higher, in order to block it from being for the ground blocking the signal. That's also something to take into consideration. Building clearances. Obviously, you're not going to shoot through buildings depending on the density of the buildings. So if you're in a high-rise downtown area, you may want to shoot it. You want to shoot in between buildings. You want to make sure that the Fresnel zone is going to be clear around the buildings. One thing I also note about the equation in the previous slide was that calculates the radius. As you can see in the upper right hand, there's an R. That means if you want to calculate the full Fresnel zone, you just double that and it'll give you the diameter. So that's also something to take into consideration. And since it's isotropic, it's three-dimensional, it is not only up and down, but it's also left and right clearance you need as well. And blockage of the Fresnel zone is additive. So if I have a tree in one area, a tree in another area, a tree in another area, all that will add together to block the Fresnel zone. Also want to take it to bridges and overpasses into considerations. If I want to shoot over a bridge, I also have to take into consideration the traffic going over the bridge, making sure that a high profile vehicle is not going to block that link through there. So let's take one example for Fresnel zones considerations. I had a customer that was deploying a security camera and access control system at the end of a 300-foot driveway. It was in the Las Vegas area. He had large, older magnolia trees lining his driveway. And it looked nice, but the thing is that the trees were additively blocking the Fresnel zone. So one tree in itself was not enough to block it, but tree after tree after tree was enough to block it. So the choices were to raise the antennas above the trees, or to mount the radios closer, or to change the frequency. We actually were not able to mount it higher or trim the trees. We weren't able to do that type of stuff. So what he did was he actually decided to go to a higher frequency, to a narrower Fresnel zone, to get around that those trees. We did have to trim the trees a little bit, because even with the smaller Fresnel zone, when the trees blew in the wind, they did block it momentarily, which could cause operational problems, so they had to trim it as well. But not as much as they would if they did a lower frequency. So let's talk about antenna type considerations. So we just talked about Fresnel zone consideration for RF line of sight, but also the antenna type you choose is also very important as well. Now, it's important to note that the antenna beam width is not going to impact the Fresnel zone. So if I get a, let's say the sector antenna 90 degrees, and I get a dish, it's not going to mean that I have a smaller Fresnel zone with a dish as opposed to the sector. The Fresnel zone is still the Fresnel zone. It's just my ability to hear interference or focus on my RF energy in a particular area that's going to be benefiting. So as you can see here, the ones with the antennas with the greater coverage is going to have less gains, less output power, less range. The one with smaller coverage is going to have greater output power. Greater focusing. So EIRP will be higher. You'll get greater range from there. For example, to read a polar plot, that's what's on the bottom here of an antenna. I would say the azimuth is the top-down view. So this particular antenna, just a rough estimate, is about 30 to 35 degrees for the primary beam width. And then for the vertical beam width, which is shown in the elevation, which is the side view of the antenna, that gives you up and down beam width, that would say it's about 5 to 10 degrees. So it's pretty narrow in the vertical, and it's pretty wide in the horizontal. So if I were to be mounting this on a pole in an RV park, I'd probably have a down tilt to that because of the vertical beam width is so narrow. So one thing to take consideration for designing for beam width is in the same point to multi-point example we showed earlier with a 30-degree beam width on the end station AC, it doesn't work if you try to expand it, like let's say to building H in this example. So building H, even though it is, let's say, a little bit further off than building Q, it's further away. So the antenna is not able to hear building H non-route, and that will give you either a poor link quality or no link quality or suboptimal, considering whatever network load you're going to be placing on the network. So that's one thing to also take into consideration. Okay, so this is a very wordy slide, but basically the gist of it is you need to make sure the antennas are separated physically so you don't interfere with each other. So if the lower frequencies need greater separation to the antennas, and also higher frequencies need less separation. Also, output power comes into play as well. If I have a higher output power and a higher frequencies, I need to make sure I need to separate it more than if it was on lower output power, because they're able to hear each other. So rule of thumb is 5 gigahertz is 3 to 5 feet, and 2.4 is about 7 to 10 feet of separation. And this is vertically and horizontally because it's isotropic. For example, in the upper left-hand corner of those two end station ACs that are like back to back, if one's on channel 161 on the left-hand side and channel 36 on the right-hand side, what I will experience if I have a protocol analyzer, it'll actually see packets where 161 show up on channel 36 because they're so physically close to each other. There's no rejection from the attenuation of the airspace. And so basically they end up being co-channel interferers. And so that means that whatever's going on one side impacts the other side. And so in order to get around that, you have to have separation. Now, it's important to note that if I had a pole and I have multiple links to go out to, I may have to, even though it calls for point-to-point connection, I may have to go to point-to-multi-point connections because of the physical limitations I have on the pole to mount to. Okay, now let's talk about channel width considerations. This is also an important topic as well. So a lot of times people like to deploy wireless backhauls with the fattest channel with the highest output power. And that may necessarily not be the best way to be deploying because you're going to be increasing the noise level, and then also you're exposing yourself to a lot more interference or higher statistical chance of interference. So for transmit channel width considerations, the benefits are if you use a wider channel. In this example, we're using Uni 1 on the 80 megahertz channel because each channel is a 20 megahertz separation on the center channel. So 80 would be a bonding of those 420s. It would be increase the throughput from a single frame. Now that's given that the environment is low, low contention. It's not really good for real-time traffic because you're aggregating multiple frames, and real-time traffic needs to have the frames sense when it transmits. So if you're aggregating them, you're introducing a latency, and that is not beneficial for real-time traffic, such as VoIP. There's less management overhead per frame in a low RF conditioned environment. So if I send multiple frames at a time, I only receive one acknowledgement for multiple frames as opposed to having one acknowledgement per frame. So that benefits the efficiency of the medium as well in the low RF contention environment. The cons is not ideal for real-time traffic. We talked about that. More overhead in high RF contention environment. I'll talk about that later. And RF energy is spread over a greater frequency area or surface area for a non-technical term. So that means as I'm taking the same RF energy, I'm spreading across more frequencies. I'm actually decreasing the amount of output power I could put on that radio because the SEC limits me to how much I could actually output. So that means that if I take the same output power, I cannot change, spread across more frequencies, that means effectively I'll have less output power, which is not good. For higher data rates. You need a higher signal to noise ratio, so you're lowering your signal ratios. So let's say, for example, I have interference on channel 48. For standard Wi-Fi channels, there's 20, 40, and 80 for AC. So let's say I have interference on channel 48. Well, then I got to drop back to 40 megahertz. That means I'm only using channel 36 and 40, which 44 is being unused at this time. If I experience interference on channel 40, that means I got to drop back to a 20 megahertz channel, and that means I'm only using channel 36 at this particular time. So in that case, in a high contention environment, you're actually hurting yourself by using wider channels than by more narrow channels. I like to view it as I like to have an analogy of a log. Let's say I have a log and I'm trying to send it through an obstacle course, those swinging punching bags. And if the rule is, if the log is, if a punching bag touches the log, signifies interference, I gotta start the log back at 0.0 and try the whole log again. So as you can see, as I try doing that with wider channels in a high contention environment, I have less statistical chance of getting that data where it needs to go, introducing more latency and loss. So a better way of doing this would be to fragment, not to aggregate, in order to get real-time traffic through. So if I break up the logs into smaller pieces and I throw them through the obstacle course, I have a greater chance of getting more pieces of the logs through than try to get the whole log through at one particular time. And that's where we have fragmentation benefiting us for real-time traffic over aggregation. So even the type of traffic you send through, you need to take into consideration the traffic type and why you want to use narrow channels over wider channels. So here's the transmit consideration to a narrow channel. You have RF energy spread across less frequency space. So that means that basically you have the same amount of energy spread across a less surface area. You have a higher signal processing on that one. It's ideal for real-time traffic, as the analogy with the log. So if I have any interference, I'm actually able to avoid the interference more by doing to a channel that may not experience that much interference as trying to bond across all of them. Less overhead in high RF condition environments. The only drawback to this is that less throughput is carried per frame. But I also have to take consideration the receive sensitivity as well, or the receive considerations on a wider and a smaller channel. So signified here with the ear as the, let's say this is the radio, and it has a 80 megahertz channel it's listening to. I'm listening to a lot of different things that are either Wi-Fi or non-Wi-Fi. That means I'm raising the noise level, which is indicative of the thermometer on the left-hand side. So I have a bigger, fatter channel, but if I have more noise, and if the signal is less because I'm spreading it across more frequencies, that means I have a smaller signal-to-noise ratio, which means I maybe not be able to maintain high data rates as effectively if I use smaller channels. So that's the reason why we like to use smaller channels for outdoor deployments, as well as lower output power, the lowest power you could get away with. Here's what would happen if I listen to a smaller channel, like a 20 megahertz as opposed to an 80. I'm actually rejecting interference on other frequencies, not listening to them, ignoring them, and only listening to what I need to listen to. So this is also the similar what I get if I use a directional antenna. If I use an omnidirectional antenna, I'm able to hear in all directions. I'm able to hear all the interference. If I have a directional antenna, I'm actually focusing my ability to hear in one area and deafening my ability to hear in other areas. And so that lowers the signal, lowers the noise level, and it allows me to hear the signal better. So if I couple this with a smaller channel width and a smaller antenna beam width, and I'm actually able to go even further. So the argument is I'm able to send little bits of information quicker, more efficiently, than I am able to send a larger bit of information less frequently. That's the argument here. Okay, let's talk about frequency considerations as well. Remember in the Fresnel zone considerations for the actual RF line of sight, it was distance and frequency dependent. So in that particular scenario, you choose frequencies based upon your RF line of sight. In this scenario, we choose different frequencies based upon its capacity to carry or interference as well to try to avoid interference. So the main reason why we have higher frequencies and lower frequencies, why the higher frequencies attenuate more than the lower frequencies, is because you have the same linear distance to go, but you have a different path distance because wavelength and frequencies are inversely related. The smaller the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. And so the car on the top is a higher frequency. You could tell it makes a lot more turns in the same 100 linear feet of road than the lower frequency car. It's doing less turns. And so if I read the odometer, the car at the top would have a greater path distance than the one at the bottom. If I were to read the gas tank as well, that means the one at the top would have less gas as it reaches the destination than the car in the bottom. And that's the reason why lower frequencies travel further, is because they have more amplitude because they have a longer wavelength. It's also important to note that most of the time lower frequencies have less capacity to carry traffic, but they do give you greater range. So we're talking about frequency considerations as well. One of the things is, how am I able to get lots of RF communication technology communicating in kind of close proximity, but not too close, they cause interference with each other. We do that through frequency separation. And within the frequency separation, and as you say, let's say we have 802.11 AF. That's done at 54 through 790 megahertz. Well, as you can see in the airplane representation, that's at the lower frequencies. So imagine airplanes flying through airspace, how multiple airplanes are able to occupy airspace. Sometimes the same column of airspace is that they're done at different elevations. Same thing with RF frequencies as well. And within the RF frequencies, they could be even further subdivided within different channels. For example, 2.4, you have 3 non-overlapping channels, 1, 6, and 11. And 5 gigahertz, you have multiple non-overlapping channels to choose from. So that's how we're able to get multiple devices operating in closer proximity to each other just through frequency separation. So now we're going to talk about the actual communication type. We have standard 802.11 and non-standard 802.11 considerations to take into account. So for the example in the upper left-hand column, corner, we have a TV and we have an infrared link for the remote control. Now that works great if you have RF line of sight. Now let's say someone walks in between you and the remote. Well, then you'll lose the ability to control the TV. So one way around that is to use a frequency that's lower than infrared. Let's say you're using 900 megahertz or something around that line, even 2.4 gigahertz. Well, then that means if someone walks through it, you can still get through them. They still have RF line of sight. You're still able to control the TV. We also have a smoke signal on the right-hand side, and let's say I want to communicate with smoke signals. Well, and there's certain situations that may not be appropriate. For example, if it's at night, it may be better to use light signals as opposed to smoke signals. Let's say it's a foggy day, it may be more appropriate to use foghorns as opposed to smoke signals. The same thing happens with the type of communication under the wireless. For example, in the bottom left-hand side, we have the standard arbitration logic for the CSMA-C8 we have for standard 802.11. Now, this is good for devices that need unscheduled access to the medium in a low contention environment. If it's low contention and you need unscheduled access to the medium, such as for real-time traffic, then that may be an appropriate use case for that particular type of technology. But let's say you have a high contention environment and you really don't have network traffic type that needs unscheduled access to the medium, then you would use something like TDMA, which is on the lower right-hand corner. And that divides it into time slots. And that means if you have something that's time sensitive, it has to wait for a time slot that may negatively impact that application. But if you don't have that type of application running on the network, then that may be an appropriate type of communication medium to use if it's a high contention. So also the mesh is involved in here as well. I didn't include a picture of it, but we talked about it in the previous PowerPoint presentation. If you're interested, you can go view that as well under the partner program, the partner portal. All right, so let's start talking about examples of point-to-point and point-to-multipoint. So this is a point-to-point example. We talked about it earlier in the slide deck. We talked about the root being down in the lower right-hand side and the non-root being in the upper left-hand side. So in this case, we're actually going over a freeway. We're actually going across different states as well. And so we have some certain challenges to this, and we have certain requirements for the link. The link requirements are, we're going about 1.5 miles. We're connecting two separate buildings together. They're light network traffic. They're not really bandwidth intensive or latency sensitive type of traffic, which is good for the link. The challenges are, we have line of sight challenges and maybe some RF interference challenges. For example, if airplanes follow this path down to a local airport, you may not want to deploy in DFS because that may impact your DFS. If you have a holding pattern for an airplane, that may change its normal pattern, that may impact your DFS as well. We also have overpasses for freeways, as you could see right here. You have tall buildings too in the way that are right here. It's a good thing that these are located in a lower valley. There's a valley that comes down and it's like a bowl like this. And so that's how the topology actually looks like. So we're lucky that we have two buildings on the top of the crest of these hills. And so you have good Fresnel zone clearance to go to them. Okay. So this is going to be an image that we got from Google Earth. So the top one will be the root point of view down to the non-root, and the bottom one is the non-root to the root point of view. You can see there's got some trees in the way, but considering the height of the secondary building and the ground topology, you got some other buildings too in the way. You got like the train depot station too. It's not really going to be that much of a big deal. And the root one also is on a higher elevation roof than the other roof, which is at a lower elevation. So we did the Fresnel zone calculations here, and it ended up being fine. He was all clear to use 5 gigahertz, so we ended up using 5 gigahertz for this one. Okay, let's start talking about point to multipoint example. Okay, so in this example, we have a top-down view. And it was condominiums, and they also have security cameras to be aware of. So we have IP camera traffic coming down here. They're doing single stream to an NVR. They're not doing any monitoring, so we don't have to worry about throughput stacking, which you have to worry about dual streams or triple streams. So that's good. It's a moderate network load because some cameras have higher megapixels than others because they want license plate recognitions. So some links need point-to-point due to the higher requirement of the camera, and some are point-to-multipoint because they're lower cameras there, lower megapixel cameras. So the challenges is line of sight challenges. We'll see in the 3D image that we do have some line of sight challenges, not quite evident as a top-down view from here. There's link capacity challenges. As we talked about that, there were some cameras that had a little bit more traffic going through them, and they were on certain edges of them, so they're aggregating. Mounting locations, we didn't have access to all these buildings. Not all buildings had a closet we could have power to it. And then possible RF challenges, which we'll show you in the 3D image coming up. So this is the same deployment, just in a different view. So now we're viewing it from the north to south, not a top-down view. And as you can see, we have certain line of sight requirements, as I was talking about earlier. For example, I can't do a straight point-to-point between building 4 and building 18 because we have this building right here, which is building A in the middle. So we have to go around that building. So that wasn't quite evident in the satellite view, but if you take a bird's eye view, you can see that more. We also have possible RF challenges due to this stadium that's on the right-hand side. So stadiums, what normally happens is that if the roof opens and they have some football games and they have some blimps flying overhead, the blimps have to have some navigation radios that operate in 5 gigahertz. And so when you deploy this, it may not have any DFS events, but when you have the event going on and that blimp is introduced, then you may have DFS events and your links will possibly go down. That's one thing to take into consideration. Also, when you have large venues like this, a lot of people gather there, and the local cell phone company may not have enough capacity on the cell phone tower to handle that, so they supplement it by trucking in mobile cell phone towers. Most of the time when they do that, they're using unlicensed spectrum called LTEU, which is mostly in the 5 gigahertz. And when they do that, you also have more interference because it's raising the noise floor on those particular levels. So if you have any 5 gigahertz links, may actually increase the noise level and may actually negatively impact your link there. So in this case, we actually used a hybrid type of solution of point-to-point, point-to-multipoint, as well as a different frequency across different links to try to get around that, around the source of RF interference. One other thing I want to point out here is that we have a building. Sorry about that. We have a building, and one of the buildings, like the one I circled in building A, is that it has an elevator shaft on the roof. And so one thing you could do in that particular scenario, which I have experience on, is if you have antennas and they need to be pretty close to each other, and you have an obstacle, a really high intensity obstacle, such as the elevator shaft on the roof, try to utilize that to the best of your ability. So if you have 4 sides, you're able to mount antennas on each side. And if the antennas don't really have that great of a beam width, you could actually get a situation in which you could actually have them on the same channel. So let me draw it out right here. So we have a building, we have an elevator shaft coming here. We have a radio on the left-hand side, and then we have a radio on the right-hand side. So what would happen is that this structure right here is attenuated enough where I can actually have them on the same channel and they're not going to be able to hear each other. Even though normally they would, in this case they're not because the obstacle is blocking them. So those are some tricks you could use, use in order to try to get the best deployment you can. So you can use structures to your benefit in this case. Okay, so now we're going to go over to the questions here. Sorry about that. And we could talk about this. Okay, so hang on a quick second. Minor difficulties there. We're going to go to the question. Let's see if we can answer some questions here. Okay, we got some questions here. We got questions on how they can have access to the slide deck. You can have access to the slide deck if you email partners at ingeniustech.com, and we will be happy to send you the slide deck. You can also have a recording if you're a registered partner in the partner program, partner portal as well. But thank you. That's a good question. Okay, we have another question here. A question about, let me see, the beam width. So the beam width, when I was talking about, is the primary beam width. How they measure that is they basically they put the antenna into an RF shielded chamber, and they grab a receiving radio. And what they do is they go around and they determine where the highest signal level they're getting on the vertical axis and the horizontal axis. So on the horizontal axis, they find the point which the strongest, and they move certain degrees to the left or right. And when they mark when it goes down by 3 dB, they mark that as the primary beam width, and that would be your horizontal beam width. As you're going up and down in that axis, that would be marking your vertical beam width, and that is only 3 dB down, which means your other steps you have down are multiples of 3. So the next step down off your primary beam width would be 6, 9, and 12, and so forth. So that's the reason why in the point-to-point type of deployment, when I had something that was 90 degrees off from the primary beam width, I was still able to make a connection, because yes, it's 90 degrees off from the primary beam width, but maybe it's only 6 dB down. So it's so close. Let's say its signal strength in the primary beam width would be negative 50, but because it's off, it's negative 56. That's still a strong signal. You still will make a really solid connection to that, and that's the reason why that will work. But if it's too far, if it's far enough away, that may not work, because of the distance and you're off the primary beam. But thank you for that question. We have another question that is asking how many bridge jumps are possible, bridge to bridge and bridge to camera. We recommend normally 3, but I've seen customers do as much as 7. It all depends when it goes back to the argument of network load and network capacity. If the network load does not exceed the network capacity, well, then you could go as far as the network capacity could take you, and the network load would be there before you notice it. So that would be the real world answer to that. But we like to just keep it to 3. We actually seen camera traffic is mostly unidirectional, and that actually survives in some pretty bad environments. I've had someone that had a cable that was just there to have some crosstalk in the cable, and so the latencies were very high. They were only complaining about the PTZ camera at the end of this 7-leg hop, because the camera was showing on and offline on the NVR. Other than that, all the other cameras are operating just fine. They're standard CMOS cameras. They're pushing traffic just fine, and he saw no frame droppage. So even though he did have crosstalk on his actual physical cable, he did not even notice the performance problem of it, because the application never required that much capacity. As PTZ required 2 ways, other cameras were just 1 way. So hopefully that answers that question. So the next question is, how can you calculate data/antenna needs with multiple cameras? Well, what you want to do is you want to see what the total throughput requirement is of the camera. That's the actual camera pushing traffic. Also, if it's a PTZ camera, you have to take it into the latency as well. There's latency requirements as well as that, especially if you have something like audio in the camera, that increases the latency requirement as well. So once you know the metrics, then you could just use the metrics, use a test like Thomasov throughput tester or something, and you could start, when you have the throughput, when you have the point-to-point or point-to-multipoint link set up, you could start pushing traffic through and testing it like that. Or you could start, having rough estimates and seeing how much a camera could push through. For example, if I do a 20 megahertz channel on 2x2, I'm estimating about 90 to 100 megabits a second of TCP traffic. So I have a camera. I want the camera to be pulling no more than 50 or 60 megabits at a time. I want to have a little bit of a buffer there. So just in case something happens, like rain or something like that, get rain fade, I'm still able to meet the requirements of the application that's running down the network. That's a good question. Thank you for that. Okay, does the rotation of the dish point to point impact the signal? Yes, it does, because that would have to go into the beam width conversation I had earlier. So if you are going off the primary beam width and going onto a side lobe, then obviously you're going off of what the focus is, and you go into like a side lobe, which is going to have you're going to have less signal than you normally would if you aligned it properly. One thing to take consideration for this as well is if I have ice buildup on the antennas, that could negatively impact it. If I mount it to something that has a lot of wind load, that could impact it too, because the wind is blowing it around, and if the beam width is small enough, that actually could be enough to cause the link to go down. So those are things you might want to take consideration for longer point-to-point links as well. There's one says, sorry about that. So we have another one that says let me see. If there's a cell tower on site, should you use 5 gigahertz 2.4 for IP cameras? Well, if there's a cell phone tower on site, and obviously that's a good question because it could be using LTE-U in the 5 gigahertz spectrum. And what they do is they say they use some protection mechanisms on the cell phone side, but cell phones are designed to be on a licensed spectrum, so they kind of have they're not very friendly when it comes to other competing things in the area. I would say you actually could use a different frequency beyond that if it's determined that the cell phone is the problem. I've actually seen cell phones cause problems in the 2.4 gigahertz. It's the way they map the information. 2.4 maps the information more towards the amplitude of the wave, and 5 gigahertz maps the information more towards the change of the wave, which is phase. And when I map information to the phase of the wave as opposed to the amplitude, I have more noise resiliency. For example, if I was in a concert and no one was around, I could talk to you and you would hear me no problem. But if there was people around and there's a concert going on, the music's blasting, I could be screaming in your face 6 inches and you're not able to hear me. So with 2.4 maps it towards amplitude, you get that problem in which you have too much noise, you lose basically what it maps it to, you lose that and you lose a lot of bits and data. And so if I were to communicate you through sign language, then I'm able to communicate with you even in a noisy environment. And that's the equivalent of what 5 gigahertz does. It maps information towards the phase of the wave. So I don't have to tell the amplitude. I could just tell whether the wave changes or not, and I could map information to that. That's why 5 gigahertz is better for noise resiliency in that particular environment. I recommend you get a spectrum analyzer and you examine the environment and determine whether or not it actually a nearby cell phone tower is actually increasing your channel utilization. And from there, I would take multiple measurements, because when you take a measurement, it's only a snapshot in time. I would take multiple snapshots and determine if it's best or not to be deploying that particular frequency. You may even have to go to different frequencies too, like 11 gigahertz or 28 gigahertz or 60 gigahertz. I think 28 or 24 gigahertz is unlicensed, and then 11 gigahertz is lightly licensed, and 60 gigahertz is also lightly licensed as well. And some cell phone towers do use 60 gigahertz as a point-to-point connection between the towers if they're close enough. Okay, that's a great question. Thank you for that. So I have another question that says, my building contains a chain where one non-route feeds the next route extending to the non-route. So you have multiple points. Two radios facing 180 degrees on different channels. So it was like the example we had there where hopefully they're physically spaced apart. My chain is 3 hops long. What needs to be considered with 2 radios close together in opposite directions on 2 different channels? How to optimize? The best way to optimize that is to just separate them either vertically or horizontally. So separate them depending upon the frequency. If it's 2.4, maybe 5 to 7 feet vertically from each other, or horizontally, if that's possible. So if you've seen telephone poles, they have something called guide arms, where their arms that stick out of the pole. That's how you would separate antennas horizontally. So you could be limited in your vertical separation, but you could still separate it in your horizontal separation in that way, if that's not too visually intrusive to the deployment. So I would say the best thing to do in this case would be to actually physically separate the radios. So you already have them in different channels, but physically separate them, use the smallest channel you could get away with, and you could go from there. One thing I didn't talk about here, which probably is consideration in the security deployment, is you want to do a tree and branch type of design. So the radios closest to the demarcation point, because it's going to be aggregating your 3 hops, is going to be carrying the traffic from all the other hops. So on the further edge, you may use 20 megahertz channels. In the middle, you may use 40, and in the closest ones, probably 80, because you're trying to put more traffic down the frequency, and so you need to extend your your frequency range. You could either do that by using wider channels in the same frequency, or what you could do is you could do a different frequency, which like a higher capacity link in a different frequency that maps it more towards the change of the wave. And so you have more changes, and so it's more noise resilient. So maybe like 11 gigahertz or 60 gigahertz or something of that nature could be what you're doing if you can't channel bond 80 megahertz and 5 gigahertz. But that's a good question. Thank you for that. Okay, I have another question here. It says, what handheld spectrum analyzer do you recommend? What frequency spectrum? So that's a good question. The handheld one, here's the thing. For handheld ones, there is some, I would say I haven't found any ones that are very cost effective. Most of the time you have to hook up to your laptop to get at least one that's more cost effective. I had a G2 air check from NetScout. That was about $2,400. That's okay. I mean, think of if you have you don't have that much requirements. You don't need to view the full spectrum. You could kind of get away with that. It shows non-802.11 802.11 utilization at that time. You could record it and send it to yourself in an email. That's good if you're like in an area where you throw it in the truck. It could be bounced around. It could be used in environments in which you can't really use a laptop in, or not ideal. It's like, for example, when I was out there in Washington deploying those point-to-point links, they had freezing rain out there, and I used my air check because of it's much more robust than my laptop. I don't really have my laptop around in freezing rain. So I would say probably might want to look into one of those. I would say if you're getting one of those, also get one that does wired as well. The problem with that is that it increases the cost significantly. Those are around $11,000 to $12,000. So those tools are only good if you actually going to have a good return on investment on it. If you're doing wireless on a regular basis, those are good for planning as well as for pre-deployment as well as after deployment for troubleshooting. For more cost-effective tools, something like a MetaGeek Insider. Either dual rainbowed would be something I would take in consideration. It has the price point is kind of high here. The device is $500. The software is another $500. It's about $100 licensing fee a year. Disclosure: I don't work for them. I don't have any recommendations. Like I don't get any kickbacks from them. So I'm not saying this just because I'm getting any benefiting from them monetarily. But that would be something I would recommend for laptop application. Then if you want to do a really good resolution one, you could do a Sidekick. That one's a little bit more expensive. It's about $2,000. With the software, it's about $6,000 total. With licensing, it gets up a little bit more. So as you can see, these things are not cheap, and I would recommend researching or getting into one if you're actually serious about troubleshooting and getting into actual planning appropriately, because you could do a lot of cool things with that. You can actually pre-qualify an environment to even tell whether or not real-time traffic will survive or not, which is good because it saves you time from deploying and headaches of troubleshooting. You could just know right off the bat whether or not it's going to be the application will be applicable to the customer, and you could do mitigation techniques before you even know about it. For example, we had a clinic that had an exit sign and it had a bad ballast in it, and we didn't know that, and they mounted the access point a little bit close to the exit sign, and they wanted some roaming, and they noticed they're having problems around that area. So we moved the access point from the exit sign like a couple feet, like 3 to 10 feet, and that improved that, so that they were able to have a connection in the area now. But it changed the radiation pattern, so now they had to add another one on the other side of the doorway so they could actually get roaming. So in that case, if we had a spectrum analyzer before they deployed, we would actually see that the exit sign was actually outputting RF energy that would be negatively impacting, and we could automatically plan for 2 other access points to get around that. I've seen a lot of things impact that. Most of the time, it's 80% of the Wi-Fi would be interference-related problems. Okay, so that's a great question. Another question is, what other tool would you recommend beyond a frequency spectrum analyzer? Well, it would be 802.11 protocol analyzer. I could do a webinar on some tools of the RF engineer at a later time, but yeah, for the probably the best two tools you have is a spectrum analyzer and a 802.11 protocol analyzer. And those two would be all you need to determine, your Wi-Fi problems or your Wi-Fi health. Once you rule out the Wi-Fi, then you start to have to look into other things like application problems on your network, such as a DHCP scope that's too small. Maybe a DHCP helper is misconfigured. Maybe an application has a timeout and doesn't know what to do with the timeout. It's wigging out, and that has nothing to do with the wireless. That would be mostly having to do with the wired side and the application itself. So you could rule that out as well, because Wi-Fi gets blamed for everything. Okay, that's also a great question too. Thank you for that. Okay, well, that's a lot of great questions there. If any other questions, that I can get to, I'll email those people directly. And we're running low on time, so thank you for your time, and hopefully look forward to the next webinar.